Good morning, students. We are discussing about your second chapter solution. Now we are going to discuss about the remaining part of the third topic, solubility, that is vapor pressure and Raoult's law. So first we have to know what is vapor pressure. So to discuss the vapor pressure, consider a volatile liquid kept in a closed vessel. So whenever we keep the volatile liquid in a closed vessel, the liquid come to the vapor phase and thereby it exerts the vapor pressure over the liquid, and that is called as the vapor pressure. Now this vapor pressure is always decreasing in case of solution. That means whenever we put solute in a liquid solvent, then the vapor pressure of the liquid solvent decreases in the solution, and that is called lowering of vapor pressure. So now you see, as solute molecules are added to a solution, the solvent becomes less volatile. Now why? It is obvious that whenever we put solute in a solvent, then this solute particle also occupies some surface position of the liquid solvent. So thereby there will be less number of solvent in that case at the surface, and we know that only the surface particle come to the vapor phase from the liquid. So when we put the solute in a solvent, then some surface position are occupied by the solute, and thereby less number of solvent molecule will be in the surface, and thereby getting less number of molecule will be coming to the vapor phase, and thereby it will decrease the vapor pressure. Of course, solute solvent interaction contribute to this effect also. Thus, the vapor pressure of a solution is lower than that of the pure solvent. If a solute is non-volatile, that is, it does not have a measurable vapor pressure, the vapor pressure of its solution is always less than that of pure solvent. So this is about the vapor pressure. So next we'll see the Raoult's law. So regarding that of the Raoult's law, two situations are arises. So there are two cases we can consider. Number one, volatile solute. That means both solvent and solute are found in vapor above the solution. That means both solute and solvent are volatile. For example, a solution of ethanol in water. So in that case, both ethanol and water are the volatile. So that means here solute is volatile, solvent is also volatile. So that is one situation. Another is non-volatile solute. That means only solvent has a vapor pressure. The solute doesn't contribute to the pressure, so there is a vapor pressure lowering. That means the vapor pressure of the solution will be lower than that of the vapor pressure of the solvent in its pure state whenever you put non-volatile solute. So now we will see both the case one by one. First, we will consider the Raoult's law for binary solution of volatile liquids. Means both the solute and solvents are volatile here. So in this case, at a given temperature for a solution of volatile liquids, the partial vapor pressure of each component is equal to the product of vapor pressure of the pure component and its mole fraction. That means the partial vapor pressure of each component is directly proportional to the mole fraction of each component in the solution. That is the statement of a Raoult's law regarding the binary solution of volatile liquids. That means here this is a binary solution, both the solute and solvents are volatile liquids. In that case, the partial vapor pressure of each component, that is directly proportional to the mole pressure of each component in the solution, or the partial vapor pressure of each component is equal to the product of the vapor pressure of pure component and its mole fraction. So that is one situation. So if the solution contain A and B, two volatile liquids, so a component A and component B, here we consider component A, that is a solvent, component B, that is a solute, both are volatile. In that case, PA, that is the partial vapor pressure of the component A in the solution, that is equal to P naught A, that is the vapor pressure of the component A in its pure state, not indicates pure state, into mole fraction of A in the solution. Similarly, PB, that will be PB naught into XB. That means PB is the partial vapor pressure of the component B over the solution. That will be equal to vapor pressure of the component B in its pure state into its mole fraction. So these are the two mathematical statements of the Raoult's law. That means A and B are the two components here. A is the solvent, B is the solute. Here PA is the partial vapor pressure of the solvent in the solution, and P naught A, that is the vapor pressure of the component, means vapor pressure of the component A means vapor pressure of the solvent A in its pure state, and XA is its mole fraction in the solution. Similarly, PB, that is the partial vapor pressure of the component B, that will be equal to PB naught, that means that is the vapor pressure of the component B in its pure state into mole fraction of B in the solution. So this is the mathematical statement of the Raoult's law. So we will see for the second case. So here PA, PB naught, PPA, PB, they are the vapor pressure of A and B in the solution respectively. PA naught, PB naught, they are the vapor pressure of A and B in their pure state respectively. Just now I am telling you. Now second case, the Raoult's law for a solution containing non-volatile solute. So in that case, at a given temperature, the relative lowering vapor pressure of a solution is equal to the mole fraction of the solute. So relative lowering of vapor pressure, what is this? So whenever we put a non-volatile solute to prepare a solution in a solvent, in that case the vapor pressure of the solution will be lesser than the vapor pressure of that solvent in its pure state. So that is called lowering of vapor pressure. And if that lowering of vapor pressure we divide by the vapor pressure of the solvent in its pure state, that will be called as the relative lowering of vapor pressure, and that is equal to the mole fraction of the solute in the solution. So that is the statement of the Raoult's law in the second case, means whenever there is a non-volatile solute in a solution. Now we will see the derivation of this, means the mathematical statement. So you see here, we know that P solution, this is the pressure of the solution, total pressure of the solution, that is equal to partial pressure of A and B. So that is from partial pressure of A and B, that means sum of the partial pressure of A and B, that will be equal to the total pressure of the solution. So that is from the Dalton's law of partial pressure, that already we know, that you have got in class 11, you recall it. So and P solution will be equal to PA naught into XA plus PB naught into XB from the Raoult's law. How? Because just now we have discussed that partial pressure of component A or partial pressure of a solvent, that will be equal to the product of pressure of the solvent in its pure state into its mole fraction in the solution. So that means PA equal to P naught A XA, that is from that of the Raoult's law. Similarly, PB equal to PB naught XB, that is from the Raoult's law. So therefore now that P solution means pressure of the solution, that will be equal to PA not XA plus 0. Why it is 0? Because we are considering here a non-volatile solute. So here, since it is a non-volatile solute, so PB naught will be 0. It is a non-volatile. So it will not come to that of the vapor phase. That means the pressure of the component B in its pure state, vapor pressure of the component B in its pure state, that will be equal to 0. So because B is a non-volatile, so thereby this part will be 0. That means the pressure of the solution, that will be equal to XA into PA naught. That means pressure of the solution will be equal to mole fraction of the solvent into pressure of the solvent in its pure state. Now XA, that will be equal to 1 minus XB. XA is the mole fraction of the component A, so that will be equal to 1 minus XB. That we know, because XA plus XB equal to 1. Here only the two components are there, A and B. So sum of the mole fraction of each component, that will be equal to 1. So thereby XA will be equal to 1 minus XB. That means P solution will be equal to this. Now if you rearrange this, then it will be P solution minus P naught A equal to minus XB P naught A. If you multiply it by minus 1, then it becomes P naught A minus P solution. Now P naught A you bring to that side, so divided by P naught A, that will be equal to XB. That means this is the relative lowering of vapor pressure. So P naught A minus P solution, that is the lowering of vapor pressure, divided by vapor pressure of the solvent in its pure state, then we call it as a relative lowering of the vapor pressure, and that will be equal to XB. That means mole fraction of the solute in the solution. So this is the mathematical statement of the Raoult's law. Whenever a non-volatile solute is there in a solution, that means the relative lowering of vapor pressure, that is equal to mole fraction of the solute in the solution. So here already I told you PA naught minus P solution, that is lowering of vapor pressure, PA naught P solution divided by P naught A, that is relative lowering of vapor pressure, and XB, that is the mole fraction of solute. So this is the statement of the Raoult's law. Now regarding that of the Raoult's law, we have got two type of solution. One is that of the ideal solution, another is the non-ideal solution. So what is the ideal solution and non-ideal solution? So that we have to know. So ideal solution and non-ideal solution, we have to know here that ideal solution means the solution which obeys Raoult's law exactly at all concentration and all temperature, that is called as the ideal solution. So that means it obeys the solution, it obeys the Raoult's law. So this is a theoretical concept actually. Practically it is difficult to have that of the ideal solution. Then the ideal solution also have the following characteristics. What is that characteristic? We have to know that heat exchange on mixing is equal to 0, and that means change in enthalpy during mixing, that is equal to 0. That means there is no change of enthalpy of mixing. Similarly, volume exchange on mixing is 0, so del V mix is equal to also 0. Now in case of the non-ideal solution, that is obviously the solution which do not obey Raoult's law are called non-ideal solution. In that case again, del H mixing not equal to 0, del V mixing is not equal to also 0. So that is the non-ideal solution. So non-ideal solution shows two type of deviation. One is the positive deviation, so this is the positive deviation in case of the non-ideal solution, and another, this is the negative deviation. This is the graphical representation of a negative deviation regarding that of the non-ideal solution. So this is the plot of vapor pressure versus mole fraction. Here whenever x is equal to 1, so that is the maximum. Now from here to here it is going on decreasing, ultimately 0. So it will go this way. So in case of the ideal solution we will get a straight line. But in case of a non-ideal solution, since it shows negative deviation, that means the partial vapor pressure of the component B, that will be lower than its ideal situation. So this is similarly for the case of the component B. So this is 0. Now if you go from here to there, mole fraction increases up to 1, that means it goes to maximum here. But it is also lesser than that of the ideal situation. So in that case we call it is a negative deviation. So thereby whenever we join these two, then we will get the vapor pressure of the solution. So in case of the negative deviation, the vapor pressure of the solution is lesser than the vapor pressure of the solution shown by Raoult's law. So that is the negative deviation. Similarly, in case of positive deviation, if you see, the vapor pressure of the solution is higher than the vapor pressure of the solution shown by the Raoult's law. So this is about the vapor pressure and Raoult's law regarding the topic solubility. So this is end for today. Thank you.